we need to select a reference node and the rest of the nodes. Select this as our reference. Node A, B, and C. One thing we can do is for node A, we have a current, 2 currents going out and 1 current going in. Going in, going out, minus I1. Minus I2. I moved IS to the other side. So this is our node equation. So we can rewrite this as this. We just rearrange some of the terms. Here's the thing about this. Look at this equation. These 2 resistors are the resistors directly connected to node A. And this resistor right here, and the voltage at node B, it's this resistor right here. So it's 1 over this resistor. And for C, it's VC over this resistor. So with that, this is actually a common practice. You can actually set up the node equations from inspection. And so I'll demonstrate. From inspection, you can see we have node A, R1, R5. So just put a minus 1 over R1 plus 1 over R5 times VA plus, it's VB, so 1 over R1 VB. There we go. Plus 1 over R5 right there, VC. And this current's going in, so we add the current. There's our node equation. So that's our first equation. The second equation at node B from inspection. Node A, node B. So from inspection at B, we can write this. We have R1, R2, and R3 connected directly to B. So I can write the B term right here. Nice. Now, we have C's connected to B through R3, and A connected to B through R1, so we can write that as such. We got this. So this is our second equation. So for node C, same thing. Okay, we have R4 connected to node C, R3 connected to node C, R5 connected to node C. We can just it writes itself. It writes itself. And there's our 3 equations. And I did that from inspection. So if you need me to show this to you, I'll show it to you. So this is node B, and I wrote down the currents, I1 going in, I4 going out, I3 going out. So we have those. So I rearranged the equation, and this guy is the same. It's the same as this. It's the same. See? The same. For node C, I2 going in, I3 going in, I5 going out, I2 going in, I3 going in, I5 going out. Here they are in terms of the node voltages. So here it is. I wrote it out, and here I rearranged it. And as you can see, it's the same. This is the same. So we can write from inspection. To solve this, all we got to do is just set up a matrix. So there's your terms. This is the A column, this is the B column, this is the C column. You know, your A, your B, your C. And here's what they equal. So just solve for these voltages and then you got it. So what's important here is that we need to understand, say that we want to find this voltage V of X. So what we got to do is basically we got to choose a reference. So let's choose one that makes sense. So what would make sense? What would be easy for us? What would make this problem very easy? If we say we call this A, call this B, call this C, call this D. Where do we put the ground reference? What would make this easy? If we let V of C equal 0, then we already know the voltage at B, and we know the voltage at C. We got it. Set your ground. We have VB equals 10 volt. From inspection, just do it from inspection. So VA is going to be this. So we have all the currents leaving of VA. So we can write this. So we have this equation, from inspection, we have all these guys connected to VA. So we know that. This connected to VB, and we have the C's right here. C, which is 0, and this goes to 10 over 500, and VD, we know VD is right there. So for the other equation, at VD, from inspection, all right, here we have this. So remember, whether or not we designate the current from D to C as going out of D or going into D, we'll still get this. We still get this because if we have VD, if VD is leaving D, if we have the current leaving D and going to C, then it's just minus VD over this guy. And that works out to this. If we had current going in, it would just be VC minus VD over this. VC minus VD over this. And the thing about that is that this is 0. So it would still be minus VD no matter which way the current's going. So now you have your equations. You have your constants here and here. So just rearrange it and solve for the current. And this is what you should get. You set up the matrix, and there's the voltage vectors, and there's the constant vectors. So your VA would be this, and your VD would be that, and VX is just VA minus VD, and that's it. Just make sure you choose your reference carefully, and it makes this easy equations. If you chose a different reference, you might have three equations, and that makes it a little bit more more involved. So it's if we can make it easy for us, why not? So let's say we have a circuit like this, something like this. So what do we do for this guy? Let's say we got to find the voltages at A and B. So that kind of just makes our job a bit easier. So what we do is called a source transformation. That's what we have to do. We have to do something called a source transformation. If you know Thevenin and Norton, this makes it easy. So here's the deal. So if you know the Thevenin-Norton theory, this is the relationship between a source transformation. So it's like whatever is right here, or whatever's right here. This right here is the rest of the circuit. If we treat this as my hand is the rest of the circuit. And we have these guys. It's easy. And so if we do it for this side, it's easy. This is just transformation, and this is the rest of the circuit. So here's your equivalent circuit. This is it. Like we got this. This makes it easy. We can easily set up the node voltages from this. It's so much easier to do this. And you can just like find the equivalent. These guys. That's just R1 in parallel with R. That's just the equivalent resistance, and same with this. So this is R in parallel with R2. So you just find that, and then you still have it. You got this. So let's say you have a circuit like this. So we can't really select like a reference node that includes both sources. So if we like pick this guy as a reference, this guy's still out there. If we pick this guy as a reference, this node, this guy is still out there too. So it's like, what do we do? What we do is something called a supernode. So here's how you do it. So we draw a boundary across the node. We have it like that, and we call this A, B, C. We have that. We have our nodes, and we pick this as the ground. Here's the key. We need to set our current flow. We have I1 flowing out. We have I2 flowing out. We have I3 flowing out of the supernode. Now we have I4 flowing out of the supernode. So the supernode equation is this. I1's leaving, I2 is leaving, I3 is leaving, I4 is leaving, equals 0. So they're all leaving. So here's what we do. So now, remember, we can also do this from inspection. If we do this from inspection, there you go. So you have your two resistors, and they're coming out of A, so those are minus. And for VC, the node C right there, because this is supposed to be one node really. And there you go, it's right there. Your R3, your R4. And for VB, it's just A is connected to B through R2, and C is connected to B through R3. And that's why there's a plus there. Now remember, VB is just VS2. It's denoted as that, but it could be an actual voltage. So what you do is you can just move this to the other side of the equation. And there you have your first equation. So what now? So here's what you do. So we see this guy. See the plus and the minus is voltage. We know that we know that VA minus VC is equal to VS2. We know that. And guess what? That's our second equation. So now we have two equations and two unknowns. So just solve like before. Set up your matrix and do all that stuff. And remember that, our V out is equal to VC. So whatever you get for VC, that's your answer. So let's say you have this circuit problem. You have your current going in. You have your IX coming out. And you have these resistors. And you have a dependent source. That dependent source is whatever IX is. So this is a voltage source, by the way. And you have another independent voltage source. This is a dependent voltage source. This is an independent voltage source. And you have your resistance. So what do we do here? Here's what I do. I just do a source transformation. So like we know that this is 1 ohm. So we're gonna have in parallel 1 ohm. And this guy, don't need this guy no more. What's in parallel with that resistor is a current source, an independent current source. And that independent current source is defined as 12 volts divided by 1 ohm. So that's just 12 amperes. So what now? Here's what now. So now we just need to find the equivalent resistance of this. And that would be 2.5 in parallel with 1. And let's just call that REQ for now. What we have here is just another run-of-the-mill problem. Don't forget, though, because we're using node analysis, use a supernode. There we go. We have A, and we have our B, and we have our C. I1 is leaving A. I2 is leaving B. I2. We have I3 leaving C, going through the equivalent resistant. And don't forget, we have our transform source, which is now our current source, going into C. So let's set up the equations. From inspection, we have these two resistors. They're connected to A. This guy is a resistor connected to A to B. So there you go. And VC, just write 0. There's no VC here. And there we have this guy. It's because we know current's going into A. So we know it's a plus current. We know we're adding a current to the equation. So I just manipulate this. This is post manipulation. I just moved it already out there. I moved it out there already. From inspection, so here's the deal. Here's the deal about B. So we have a current going into B, and we have a current going out of B. Here's the thing, though. We have the supernode is right on B as well. So when I say that we're doing, from inspection on B, we're actually doing from inspection on the supernode because B is part of the supernode. So when I say B, we're doing the supernode. So this is the supernode equation. So we have our plus because the current is going into the supernode. I1 is going into the supernode, so that's why we have this. And I2 is leaving it. And that's why we have, okay, so this guy, that guy is because the I2 is leaving. And this guy 1/2.5 is from this relationship VA minus VB over this resistor. So now for the equivalent, R1 over equivalent, that's just these guys in parallel, these resistors in parallel. And since it's leaving, we have a minus. So this guy's minus 12 because we have this current source going into it, and it's minus 12 because I moved it to that side of the equation. So we have two equations, but 3 unknowns. So where's the other equation? Here's what it is. If we have VC, there's a plus. Think about this: the plus minus. Remember, plus minus. VC minus VB is equal to IX. And IX is just equal to VA over the resistor, which is 7.5. You have your one equation, you have your two equation, and you have your third equation. So 3 equations, 3 unknowns, set up the matrix, plug and chug. There you go. There you have it. There you have your node voltages, and you're done. You solved it. Congratulations.